G'day, welcome to lesson 3 on our Equilibria unit. Today's lesson, entitled Applications of Chemical Equilibria, we are going to apply the concepts of equilibria and equilibrium constants to laboratory procedures, including industrially with the Haber and Contact processes. The learning outcomes from this unit 7 we'll be addressing in this lesson just below there. So we've introduced many concepts. In the lesson just before this, we were looking at this idea of the equilibrium constant, how to calculate that, and what that tells us about where the equilibrium lays in a chemical reaction. We're going to continue on very naturally from that point and look at some specific kind of laboratory applications of this equilibrium constant. So we had our Kc if we're dealing with the equilibrium constant from concentration, or Kp if that is from partial pressures. Alright, so the equilibrium constant we said is a molar ratio of products to reactants when a reaction is at equilibrium. And we discussed K as a measure of where the equilibrium lies. So we can calculate the value for K depending on the concentration of each respective reactant or product. And then if that K is less than 1 or if that K is greater than 1, that tells us quite a bit about our reaction. So if K is less than 1, our concentration of reactants exceeds the products. That tells us that our reaction hasn't occurred very far to the right at all. We've got mostly reactants left, and then the closer to 0 that is, the less that forward reaction has occurred. So the closer to the 0, the more the concentration of reactants exceeds the concentration of the products. Conversely to that, if K is greater than 1, the concentration of the products will exceed the reactants, and then the bigger the number is, the further the reaction has gone to completion. Excellent. So we can use these equilibrium constants to determine the concentrations of reactants and products. And we use these things called a Rice table. So a lot of times we can get an equilibrium constant, we can get that data at a certain temperature because these are unique for certain chemical reactions and these have all been done and documented and logged and you can look them up very easily. So if we have a known amount of reactant concentration or reactant pressures, we can use the known equilibrium constant to determine how much product we should expect to get. And this is very useful because, as chemists, a lot of the time when we're doing these things in labs, we want to get product. We don't really want to have reactants left over. We want to get the equilibrium as far right as we can in order to get as much product as we can because we already have the reactants because that's what we use them to make the products. So hopefully that makes sense a little bit. So we use this Rice table. Rice, delicious rice, stands for R for reaction, I for the initial concentration or the initial pressure, depending on if you're doing Kc or Kp, C for change, and then E for the equilibrium concentration or the equilibrium pressure. Let's do an example of how we use these. All right, we have a reaction here. We're reacting this and this to get that. The initial mixture contained so much concentration of each of those, and at equilibrium we had a concentration of the product. Determine the Kc of this reaction. All right, so Rice, the first thing we want to do is write the reaction down. So let's go to our whiteboard and let's do that. This reaction looks like this. CH3, CO, CH3 plus HCN at equilibrium to CH3, COH, CN, CH3. Excellent. All right, this is our reaction. This is R. All right, I, the initial concentrations. We're given that data in the question. The initial mixture contained concentrations of that 0.05 for that species and 0.05 for that species. Let's write those down. So the initial concentration for this one was 0.0500 mole per decimeter cubed. Our initial concentration for this one was 0.0500 mole per decimeter cubed. Let's consider our initial concentration for our product there. Well, it's the initial. So when we're doing a chemical reaction, we start with the reactants, and then at the very start, we don't actually have any product yet, do we? It's all reactants. It's all the concentration is from the reactants. So our initial concentration for our product, well, it's the initial. We haven't actually made any yet, have we? So this is 0. We haven't made any of that yet. Moles per decimeter cubed. Great. So we got it like that. Now we have the C. C stands for change. So this is the change from the initial concentrations or the pressures to the equilibrium concentrations or the pressures. So let's see what the data was given for the equilibrium. At equilibrium, we had that much of the product being observed. So I can put this data into this point here. So at equilibrium, I had 0.0233 moles per decimeter of the product. So we've got to work out the equilibrium constant, and we can write the equilibrium expression by doing the concentration of the products over the concentration of the reactants at equilibrium, because that's what K means. It means at equilibrium. But we don't know the concentration of the reactants, do we? So that's why we're doing this Rice table. So let's put the change in. The change in the concentration of my product is this one here. This is going from 0 to 0.0233 moles per decimeter cubed. So my change is 0.0233, like that. Now, we can use the stoichiometric relationship to determine what the change of the reactants is going to be to get the equilibrium concentrations. Because what this is saying is that we started with none of this and we've ended up with that much, so we've had an increase of that. Now, for every one of these, there is one of those and one of those. So what this is saying is that if we're making a change of 0.02333 here, because of the stoichiometric relationship between these three, this has to be the same change as here. Only we're using this up, aren't we? Because these are the reactants. The concentration is decreasing the reactants and increasing of the products. So if this is a 1-to-1 ratio of that, it means we're decreasing by the same amount that we would be increasing over here. And the same with this one here. This is a 1-to-1 ratio there, so we're decreasing by this same amount. Because it's just a 1-to-1 ratio. So it's saying for every one of those and one of those come together to form one of those. So now we've just got to simply calculate our new values here. So at equilibrium, my concentration of this one will be that minus that, which is going to be 0.0267. Yeah, that's going to equal 0.0500. Cool. And then that means that's going to be the same one for this one here, 0.0267 moles per decimeter cubed. So what we've done is we have used the initial concentrations, which we would have measured in the lab. We can get the equilibrium concentration of our product, which again has been a measured piece of data. And then based on what we know about equilibrium and the stoichiometric relationship, we can determine what the equilibrium concentrations of each three of these species are going to be. From there, we can very simply just plug that into our equilibrium expression. So I got to write the equilibrium expression for this one here, which is going to be the concentration of the products. I'll write it all out. CH3COH CnCH3 divided by the product of the concentration of the reactants, CH3COCH3 times by HCN. I've now got all these numbers here. So I'm going to plug each of those into the calculator. I've got a product concentration of that, so 0.0233 divided by that times that for these two here, 0.0267 times 0.02267. That's going to give me a value of 32.68339. All right, we'll deal with significant figures and we'll also deal with units. Now remember, when we're dealing with equilibrium constants, you have to work out the units each time. So you just do that by simple cancelling. That top one is going to cancel with one of those bottom ones. So we're going to be left with units of 1 over, is that still in frame? Yeah, 1 over mole per decimeter cubed. And that's going to invert the sign of each of these exponents. So we'll end up with mole minus 1 decimeter cubed. If you need a recap on cancelling out units, go see the previous video in this series. All right, let's go back and have a look at our significant figures. We've got 3 there, 3 there, 3 there, 3 significant figures. So I'm going to write an answer of 32.7 moles to the minus 1 decimeters cubed. So let's think about what this is telling us. This is a number that is greater than 1. So this is telling us that at equilibrium, our equilibrium is lying to the right-hand side. So we got more products than we do have reactants. And if we check it against here, we should get 32.7. Excellent. All right, your turn. Why don't you have a go? I got a couple of examples here, one involving concentration, one involving pressure. The following reaction was undertaken. If the initial concentration of H2 and CO2 were both 10 moles per decimeter cubed, and the equilibrium concentration of carbon monoxide was 9.47 moles per decimeter cubed, determine the Kc for this reaction. Why don't you give that a pause? Give that a go, and you can check it when we go through it now. So the first step, we have R for reaction. Let's write the reaction out. Hydrogen gas plus carbon dioxide gas reaches an equilibrium with water vapor and carbon monoxide gas. Great. We have some initial concentrations. These are both 10.0. I'm not going to write units. You should probably write units, but I'm just going to do it nice and quick. And then it's the initial, so we haven't formed any of this yet, so these are going to be 0 because it's right at the start. And then at equilibrium, we have 9.47 here. Nope, I lie. We have 9.47 for the carbon monoxide. Lovely. Let's work out some concentrations. So if we look at the change here, we've gone from 0 to 9.47, so we are going to plus 9.47 to this. This is at a 1-to-1 ratio with that, so that means that it's increased by the same amount, and this one's also increased because it's on the product side, so you're making the product, so you're going to make 9.47 of that as well. Now, the change, this is plus 9.47 because this has decreased in concentration because this is the reactant side. This is what's being used up. So we look at the ratio, also 1 to 1 to 1 for all of these. So these are going to decrease by the same amount that these have increased. We're going to see some examples later on where it's not a 1-to-1 ratio, and we'll go through that. But for now, we just have the same numbers, just decreasing over here instead of increasing over there because that's on the reactant side. Then we do all our quick math to get our equilibrium concentration. 0 plus 9.47 is going to be 9.47 moles per decimeter cubed. And then if we go 10 minus 9.47, we're going to end up with 0.53 for both of these. Great. Now we want to calculate the equilibrium constant. Let's just have a think about this for a second. What do we expect the Kc value would look like? If Kc is a ratio of products to reactants, and we've got a lot more products over here than we do reactants over here, we would expect our Kc here to be a number greater than 1. Yeah, because we can see the equilibriums is lying strongly on the right-hand side here because we've got a lot more of the product. And because we've got a lot more of the product, in fact, we would expect the Kc to be quite a big number. So hopefully that is what we will see when we plug in all of our data. So let's do the equilibrium expression, the concentration of the products divided by the concentration of the reactants multiplied by each other. And then it's just a matter of plugging in these numbers. So we have 9.47 times 9.47 for these two, for those two, and then divide that by 0.53 times 0.53. I get the calculator. We should have a pretty big number divided by 0.53 times 0.53. And I end up with a number of 319.26. Now we just have to check significant figures. How many have we got? We got 4 here, but we got 3 there. So we're gonna have 3 significant figures, and we have to think about units. Remember, every Kc value is going to have units that are unique. So we're gonna have 2 moles per decimeter cubed on the top, 2 moles per decimeter cubed on the bottom. They're all going to cancel out with each other. We're going to end up with no units, so that will give us a value of 319 no units. And that is what we predicted. We predicted a large Kc that is greater than 1. We check that over here. That is indeed, hopefully, what we get. Cool. Here is a second one you can have a try at that is dealing with pressures instead of concentrations. We have the reaction there. The initial partial pressures of H2 and I2 were those two numbers respectively. At equilibrium, the partial pressure of H2 was that, and Hi was that. Determine the Kp. Give it a pause, give it a try. It's the exact same process, only instead of dealing with concentrations, you're dealing with pressures, but exactly the same set out in a rice table. Give it a pause, and then why don't you check your answer when you push resume now. So R, as always, stands for reaction. I'm going to write my reaction here. I have H2 plus I2 going to 2Hi, and it reaches equilibrium. Initial concentrations were given to me. We have a value of 7.27, was it? Yep, 27 times 10 to the 6 pascals. We're dealing with pressures now, so our units are pascals as opposed to moles per decimeter cubed. 4.22 times 10 to the 6 here, pascals. That reaches equilibrium, and we end up with, oh, well, this is the initial reaction, isn't it? So at the very start of the reaction, we haven't formed any of this. So that's 0 pascals. At equilibrium, we were given the values here for 3.41 times 10 to the 6 pascals. That was unknown, and over here was 7.72 times 10 to the 6 pascals. All right, now, exact same process. We've got to work out the change. Only this time, we have a 1:1:2 ratio as opposed to a 1:1 to 1:1 that we had last time. But it's still pretty straightforward. So if we look here, we've had an increase of 7.72 times 10 to the 6. Yeah, 0 to that is going to be an increase of that. Now, let's think about this a few ways. This is saying that for each of these, we are making 2 of these. So if one of these makes 2 of those and we have an increase of that much, well, we're only using one of these to make 2 of those, aren't we? So our increase here is going to be half the amount. Hopefully that makes sense. We've got the 1:1:2 ratio, so if we have an increase of that much there, but this has twice the molar equivalence as that, so our change here is going to be half the amount. So if I divide that by 2, I get a value of 3.86 times 10 to the 6 pascals, yeah? So if there's one of those for every 2 of those, we're going to have half the decrease for the increase that we see over here. And we can double check that because 7.27 plus 3.86 is going to equal, oh no, other way around, sorry. 7.27 minus 3.86, I gotta remember my minus signs, is going to equal 3.41, and that's in fact what we've observed here. So there's 2 ways that we can check that. Now, this is the same ratio, 2 to 1 over here. So we're gonna have the same decrease, 3.86 times 10 to the 6, like that. And then if I very simply plug that into my calculator, I get an answer of 0.36 times 10 to the 6 pascals for my partial pressure here. There's in fact another way that we can consider this. We talked about the idea of partial pressures and total pressures, and we said that the total pressure of a system is simply adding all of the partial pressures of the system together. So if we look at the partial pressures at the initial, we have this and this and this. Now we've all got conservation of matter. It's a closed system. None of our matter is going anywhere. So if I get the total pressure of the system here, 7.27 plus 4.22 plus 0 times 10 to the 6, 11.49 times 10 to the 6, and if I add up all of the pressures here, I should end up with the same values. 0.72. I end up with the same value here, 11.49 times 10 to the 6. So in fact, we very simply could have gotten the equilibrium partial pressure here by just minusing these 2 values from the total pressure that we established at the top. So a few ways that we could undertake that. But now that we do have our partial pressures, let's punch it in our equilibrium expression. So I'm going to write out my equilibrium expression. Kp is the pressure of my product. Now we do have a squared here of the Hi divided by the pressure of H2 times by the pressure of I2. Yep. Then we just got to plug our numbers in. We got 7.72 times 10 to the 6 squared divided by 3.41 times 10 to the 6 multiplied by 0.36 times 10 to the 6. And we should end up with a value. Well, why don't we predict what the value is going to be? Which side is there more pressure on, the products or the reactants? We have a higher pressure over on the product side. So we're going to expect a Kp to be greater than 1. So if I plug all this in, 7.72 times 10 to the 6, talk amongst yourselves, squared divided by 3.41 times 10 to the 6 times by 0.36 times 10 to the 6. We get a value of 48. Well, let's look at significant figures. We have Three significant figures, three significant figures, three. We're going to have three significant figures in our answer. We were given all three significant figures in the question, so 48.5. And the units, we're going to have pascals times pascals, because it's squared, over pascals times pascals, because there's 2 on the bottom. They're all going to cancel out. No units. How do I spell units? 2, 3 significant figures. Excellent. And if we check over here, that should hopefully be the answer that we see. Excellent. 48.5 is correct. All right. Let's scale up now. Let's talk on an industrial level. Now, when you're talking on an industrial level, you're talking about making vast amounts for some sort of use in industry. And I mean, there's countless applications for chemicals when you're synthesizing them at an industrial scale. So we're going to talk about 2 very important reactions in specifics. The first of which is the Haber process. The second of which is the contact process. All right, the synthesis of ammonia via the Haber process. Mainly used to produce fertilizer. This is very important because by mass producing fertilizer, it means that we can mass produce food to support lots and lots of people. Whereas without this sort of mass production of fertilizer, we couldn't grow the crops we need to support the food for as many people as we currently do support it for. Developed by the German chemist Fritz Haber, who was a pretty interesting fella, and Carl Bosch, sometimes called the Haber-Bosch process. And it looks like this. Nitrogen plus 3 hydrogen is at equilibrium with ammonia. We have a delta H of reaction of minus 91.8 kilojoules per mole, so we have an exothermic reaction. Consider the effect of equilibrium. Now, we talked about how we can manipulate the position of equilibrium using Le Chatelier's principle, and there was 3 factors: concentration, temperature, and pressure. So if I'm mass producing ammonia on an industrial scale, we want to try to make as much of it as we can. So we want to push the equilibrium to the right as far as we can. However, there are lots of trade-offs. If you think about things like having high temperatures or having high pressures, these can be very expensive processes to accommodate that. So to have a high pressure system is going to cost my company that's making ammonia a lot more money than having a low pressure system. Having a high temperature, the same sort of thing. So there are trade-offs here where we can push the equilibrium to the right, but we also want to do it in a cost-effective manner. And there is also the extra factor of reaction rates. We're going to look in the unit after this how things like temperature and pressure can affect reaction rates. So that's another thing that we've got to bear in mind as we consider these. But let's just talk purely from how it's going to affect the equilibrium. If we increase the pressure, what is going to happen to the equilibrium? Have a think, maybe pause it if you need that time, and then check it. What's going to happen is increasing the pressure, the system's going to want to change to decrease the pressure. It is going to shift to the side with less molecules. We have 1 plus 3, we have 4 gas molecule equivalents on the left-hand side, 2 gas molecule equivalents on the right-hand side. Equilibrium is going to push to the right-hand side. We're going to increase the amount of ammonia we make. So on an industrial scale, if I wanted to make lots and lots of ammonia, I would want to do this reaction under a high pressure. But like I say, having a high pressure is going to cost the company more money to do that. So do I want to have the high pressure if it's going to cost more, or is there another way that I can manipulate the equilibrium to make more ammonia? And it's all about these sort of balancing the cost and the benefits. What about decreasing the temperature? Pause, have a think, and then check it. When you check it now, it is going to want to increase the temperature. It's going to favor the exothermic direction. So decreasing the temperature is going to push the reaction. It's going to push the forward reaction because that's exothermic. We're going to make more ammonia and shift the position of the equilibrium to the right. However, decreasing the temperature does decrease the rate of the reaction. So even though we're going to make more ammonia, we're going to make it slower. And that's another cost benefit thing that's going to have to be weighed up. But reaction rate is coming. Don't worry too much about that now. That will be a few videos down the track. What about removing NH3? Pause, have a think, check the answer. If we decrease the concentration of the products, equilibrium is going to shift to increase the products. We're going to shift the equilibrium to the right-hand side. So that's another thing I can do whilst I'm making my ammonia. If I'm taking out the ammonia from the reaction vessel as I'm producing it, that's going to shift equilibrium. That's going to make more of my ammonia. Let's look at our other one, our contact process. This is part of the synthesis of sulfuric acid. And sulfuric acid has a number of uses, also used in fertilizers. used in the manufacture of chemicals, lots of things that we can use sulfuric acid for, so it's very important. Developed by British vinegar manufacturer Peregrine Phillips. Great name, Peregrine, I like it. Looks like this, 2SO2 plus O2 goes to 2SO3. So this is a step in the production of sulfuric acid. Very exothermic. You can see big negative number. Let's do the same thought experiments. Consider the effect of equilibrium on the following. What would happen if you increase the pressure? Well, the system's going to want to decrease the pressure. It's going to shift to the side with less moles. We have 3 gas molecules on the left-hand side, 2 gas molecules on the right-hand side. We're going to create more SO3, which is good. But again, increasing pressure, cost-effective thing to do. And in fact, we already have such a high Kp value that we don't necessarily have to do it under high pressures because it's already such a equilibrium towards the right. So in fact, this part is just done under atmospheric pressure because that's going to be cheaper and we don't have to spend all that money putting that high pressure in because we're already making so much of it. What about decreasing the temperature? Same as over here. It's going to favor the forward reaction because the forward reaction is exothermic. Exothermic is going to increase the temperature. Le Chatelier's principle states that the system will counteract it. So if you're decreasing the temperature, it's going to want to increase the pressure, increase the temperature, and it's going to shift the position of the equilibrium to the right. What about removing the SO3? You can do that by absorbing in 98% sulfuric acid. And that will also shift position of equilibrium to the right, but the same sort of thing, because we already have such a high Kp, it's not really that necessary of a step. Lovely. Last little bit today. Let's do one last question to have a go at one of these rice type questions with the Haber process on an industrial scale. Pause now if you want to have a go. Here's the question. The Haber process is undertaken with 120 moles of hydrogen gas and 40 moles of nitrogen gas. So big, high scale process. Equilibrium was achieved with the total volume of the mixture equaling 1.0 decimeters cubed. If 20% of the reactants were converted into ammonia, determine the Kc for this reaction. Pause now and then check it. As we always do, let's start with writing the reaction. So we have N2 plus 3H2 reaches equilibrium, 2NH3. Okay, we were given initial concentrations of 120, well, we were given 120 moles, and it's in a 1 decimeter cube vessel, so it's just 120 moles per decimeter cubed. 120 moles per decimeter cubed there. Nitrogen was 40 moles per decimeter. And then at the start of our reaction, we haven't made any ammonia yet, 0 moles per decimeter. This was worded a little bit differently, wasn't it? It's saying if 20% of the reactants were converted into ammonia, what's the Kc? So if 20% of the reactants were converted, it means that 80% of the reactants are left. So I got to get 80% of my reactants, and that will tell me my concentration equilibrium. So I go 40 times 0.8. That gives me an equilibrium concentration of 32 moles per decimeter cubed. So this has a decrease of 8 moles per decimeter cubed. Over here, we're going to have 3 times that because it's a 1:3 ratio. So for every one of those, we're using up 3 of those. So if we have a decrease in concentration of 8 there, we're going to have a decrease of 3 times that because we're using 3 times as much to get minus 24 moles per decimeter cubed there. And then over here, if this is a 1:2, we're going to have an increase by double that. So I'm going to plus 16 moles per decimeter cubed there. That's going to give me some equilibrium concentrations equaling 96 moles per decimeter cubed and 16 moles per decimeter cubed. Now we've got to do our equilibrium expression. My Kc is equal to the concentration of NH3 squared to the power of 2 divided by concentration of nitrogen times by concentration of H2 to the power of 3 cubed. Yep. So let's plug in those numbers. We're going to have a value of 16 squared, 16 times 16, that's going to give me 256. And then we're going to have 32 times by 3 lots, so 96 times 96 times 96. All right, I'm just going to do it like this. We're going to go 16 squared divided by 32 times 96 to the power of 3. And that gives me an answer of 9 point, well, how many significant figures? We've got 2 significant figures, 3, 3. So let's put this in 2 significant figures. So that's our least precise one. So it's going to be 9.0 times 10 to the 1, 2, 3, 4, 5, 6. 10 to the minus 6. Now we've got to work out the units. So I might write this out the longhand to make this one a bit clearer because it's quite a few units that are going to cancel out. So we've got to make some space here so we can see what we have. I've got 2 lots of moles per decimeter cubed on the top. Moles per decimeter cubed times moles per decimeter cubed, because there's that to the power of 2. Then I've got 1 for the nitrogen on the bottom, moles per decimeter cubed, and then 3 for the hydrogen. So moles per decimeter cubed, 1, 2, and 3. All right, let's see what cancels out. That's going to cancel out with that. That's going to cancel out with that. We are left with 1 over 2 lots of moles per decimeter to the minus 3. But we can simplify that even further. Because if we got a mole times a mole, we're going to end up with mole squared. And then decimeter to the minus 3 times decimeter to the minus 3 is going to be decimeter to the minus 6. But then I want to get this without the fraction form, so I can use my power laws. If I make these signs the opposite, we will end up with moles to the minus 2, decimeter to the minus 6. So all of this to say, this is going to be 9.0 times 10 to the 6, 10 to the minus 6, moles to the minus 2, decimeter to, no, moles to the minus 2, decimeter to the 6, because we're inverting that number, aren't we? We're making that a minus to a positive. Excellent, many steps to the reaction, and this is telling us our Kc is very, very small, so we're not forming very much product at all, are we? Let's check this over here, and we do indeed end up with that for an answer. And with that, we have finished the lesson. What have we done? We've calculated the quantities present at equilibrium given appropriate data. Such calculations will not require the solving of quadratic equations, so there are other ways to solve these types of equations here that involve quadratic equations, but that does not concern us in this particular course. And then describe and explain the conditions using the Haber process and the contact process as examples of the importance of an understanding of chemical equilibrium in the chemical industry. Tasks, as we always have, if you'd like to consolidate some understandings, pause 1 column at a time, working from the bottom and making your way to the top. Thank you. I will see you next time as we continue and finish off our unit into Equilibria. Have a good one.